Right, so we need to get Leigh connected up then. Oh, I'd say no, they're still so early, it's half an hour early. Just say nah.
Is that it?
No, just leave them in there.
Just want to know.
Right, Leigh, how do we connect you then? Laptop?
Should be, I think, yeah.
And we'll move the,
That's my
move
daughter
the
on
screen
there.
down
So
as
Oh,
well.
beautiful.
let's get rid of that. Yeah. So those people.
Which button is
so
it
those
to
people
put the
not
screen
concerned
down?
about what they've walked into.
It should come on automatically if you project
Really?
it on, yeah.
Oh, no, actually.
I came in and that was already on, so we didn't. Oh, there we go.
So do I have to close to get
What are you trying to do?
just PowerPoint? So just that off. It would have been great to keep it open, but if I have to close, then I have to close. Now it's us, and we just need to switch to
Show screen.
Share screen on there,
Yeah.
maybe?
yeah.
If you share screen on there, that'd be great.
Yeah.
That's all we've got, isn't it? We want to get to.
Do you want the screen?
I mean, has it recognised the laptop first off on
It
this?
did.
It did a minute ago, didn't it?
It had, yeah, it did. It had your daughter on it, didn't it?
Yeah,
So
yeah.
it's reconnected.
And then it's just gone off again.
Maybe
What-
share leave, close that.
Where is your daughter? On
She's
the
the
computer?
desktop saver
She's the desktop.
desktop. So I think
Is this extended then? Is this have you got like an extended desktop? Right?
yes, I have.
Can we change it? I don't know how to do it on a Mac. Can you change it so the same thing is displayed on both screens?
Don't know that I can. Let me should do it.
Yeah. Okay. Well, welcome to those in the room and those joining us online to today's talk. It's a great pleasure and honour to welcome Dr. Dr Breen from Birmingham University. He's going to give us a talk on diet and protein with skeletal muscle in mind, with implications for health and disease, but more importantly, more specifically, we're going to Leigh is going to talk about the research of Professor Kevin Tipton, who, unfortunately passed away in January of this year. I'm going to leave Leigh to discuss Kevin and his work in more detail because he's a better place to do that. But I'll just give you a quick introduction to Leigh. Lee's, as I said, joining us from Birmingham University, where he worked with Professor Kevin Tipton. Lee's a leading expert in the field of skeletal muscle metabolism, with his group renowned nationally and internationally for their work in the molecular and metabolic regulation of skeletal muscle plasticity in health and disease, as well as having a specific expertise in the roles of dietary protein as a key regulator in muscle protein synthesis. So that's very much why Leigh is here to give us a talk today. So without too much from me, I'll pass you on to Dr. Leigh Breen.
Thanks, Richard. Hopefully everybody on the Zoom call can hear. I've not had any, I can't see any thumbs down or complaints at the moment. So I think everybody is good. There's nothing in the chat, so I'll keep going. Yeah, thank you for the invitation, Richard. And it was a great pleasure to come down to talk about the work of Kevin Tipton. So I've got quite a challenge here today. So I'm hoping to deliver some information to inform you in general around the role of diet and exercise on the regulation of skeletal muscle protein turnover, and hopefully highlight the key implications for exercise performance, adaptation, and health. But also, I want to try and frame this entirely around the work that Kevin produced over a near 30-year career. Kevin was considered to be an international leader in the field of skeletal muscle protein metabolism, renowned by all the groups who do this work globally. Kevin's research outputs over the year have set the agenda for muscle protein metabolism research for groups that have emerged subsequently. What set Kevin apart from most other people, I think, in this field was his discerning nature when it came to research, never afraid to critically appraise his own preconceived notions and challenge his own beliefs, and also the unwavering support that he offered for his graduate students and other trainees, and his engaging and enthusiastic presentation manner, which has helped to inspire not just those he trained directly, but pretty much anybody he came into contact with and taught over many years. To provide a little bit of a historical perspective before I talk about the work of Kevin, prior to his emergence on the scene in the mid-1990s, a couple of decades previously, throughout the 1960s into 70s, developments in microscopy and also biochemistry techniques had confirmed the plasticity of skeletal muscle, or its malleability in response to specific contractile stimuli. So, for example, the intensity, the duration and frequency of a contractile stimulus on skeletal muscle would induce divergent phenotypic responses or remodeling in that tissue. Sometime around the late 70s and the early 80s, there were advancements in mass spectrometry techniques and also the development of mathematical models as well, which now allowed researchers to directly measure skeletal muscle protein turnover and intracellular and extracellular flux. So yeah, I trained under Kevin Tipton, and I think I'm right in saying, Richard, that a few months ago, maybe a year ago, Kevin was invited here to come and speak to you directly, and had agreed in principle to do that, but ill health prevented it. So unfortunately, you've got a poorer version of that in me, but hopefully somebody who is hoping to follow in Kevin's footsteps in terms of research output and general interactions in research and academia as well. So, just get my pointer working again. Screen seems to have frozen. Of course it has. Here's a brief overview of the career path of Kevin. So he didn't enter nutritional sciences and human exercise physiology by a conventional route. Started out as an undergraduate and postgraduate, really focused on zoology before completing a PhD in nutritional sciences, and then moving to the University of Texas Medical Branch under the supervision or the guidance of Professor Bob Wolf, a noted expert in muscle protein turnover and applications of stable isotope tracers. And it's during his time at UTMB as a postdoc and then assistant professor that things really started to develop in terms of research outputs that were later seen as seminal in this area of work. Then to the University of Birmingham, and then on to Stirling as a professor, and finally a short tenure at Durham University before retirement. It's impossible really to talk about the work of Kevin without touching on his passions as well. They were intrinsically linked with the work that he did and the way he communicated as well. So I won't go overly sentimental with this talk because Kev probably wouldn't have necessarily appreciated that. But here are a few images highlighting some of Kev's passions. So time as a zoology student spent on a Russian fishing trawler. A keen athlete and sportsman. Passionate about rugby in particular, and also a very competitive distance runner back in the day. Always one for a walk, particularly with his dogs. Passion for his dogs over the years, and always keen to barbecue and host a party in any weathers. And finally, super proud to become a British citizen a few years ago, and even wore his kilt, as you can see, to the ceremony there as well. But for a little bit more information on Kevin, 3 of his closest friends and colleagues over the years, including his first PhD student and a former colleague of mine, Oliver Witard, I've published recently a really nice short perspective in IJS NEM to detail a little bit more about Kevin's academic journey and some of his professional accomplishments, and well worth a read, I think. So I met Kevin in 2007. The top images are taken throughout my research masters. I was at Manchester Metropolitan University at the time, and it's probably just as well. This image is really grainy and you can't see very well because it's me hosting a boxercise session for a group of older adults. So I was tasked in my research masters with taking a large group of older adults and having them go through 4 months of resistance training to try and increase strength and muscle mass. And parts of this training program included boxercise and balance and flexibility alongside more conventional targeted strength training as well. And during this time, I became intrigued by the plasticity of skeletal muscle in these individuals, both in terms of how they presented when they arrived at the lab, often quite far deconditioned with poor functional ability, and also how they responded to a structured strength training and protein nutrition intervention in terms of improving muscle mass, strength, and function. In some individuals, we saw great improvements. In others, not so much. Some people even went backwards, believe it or not, in some of the parameters. So I was trying to understand as an MRes student some of the mechanistic regulation of skeletal muscle protein turnover. And inevitably that led me to Kevin's work, especially some reviews that he'd published and some original papers focusing on muscle protein turnover in older adults and the role of physical activity and diet in supporting lifelong muscle health. So I initially reached out to Kevin to ask if he had a position available for me because I discovered he'd moved to the University of Birmingham. Thankfully, there was something on offer, so I went into interview. I was incredibly nervous to meet, I guess, my first science hero, and but thankfully got the job despite those nerves. And this is the group as it was back in 2007, 2008, I think, the Exercise Metabolism Research Group at the University of Birmingham, headed up by Asker Ukendrup, again, strong presence of Anton Wagenmarkers and Kevin Tipton here centrally. Great times. We were left relatively free to conduct the science we were interested in and wanted to run. So here's an image of us during a muscle biopsy procedure for one of my studies. And Kev, back in those days, was the trigger man on the biopsy. So we had a lot of fun during those sessions. And often the conversations we had during those biopsies, we'd get a lot of great nuggets of information from Kevin. So anything from sport, politics, history, he'd kind of hold court and teach us all about these things. And we try and get any snippets that we could as we were educated. A quick word cloud of Kevin's research outputs over the years spits out something that looks a little bit like this. Again, I had to truncate the words here, or else this could have just spun and spun and spun. But I guess, true to form and what most of us would associate with Kevin, he's a protein guy, an exercise guy, a muscle protein synthesis guy. So the big key words that appear in his papers here are again what we would all typically associate with Kevin's well-recognized research output over the years. But and again, sticking true to form, I'm going to focus most of my talk around the work that Kevin was predominantly known for over the years. But what I don't want to do is to take away from some of his other significant research contributions in other areas over the years. So fantastic studies on dietary protein to optimize weight loss or promote high quality weight loss. That is the preferential loss of fat over muscle tissue. Some work on metabolic health, endurance exercise physiology, working with alternative tracers to study glucose metabolism. And during his tenure at Sterling, some really important work done on the muscle anabolic properties of fish oil as well. So I've not included any research metrics here. H-index citations, you all know where to go to find those things. I didn't include them because I know that Kevin didn't like those metrics an awful lot, not just his personal metrics, but perhaps maybe the toxic way in which research institutes sometimes use metrics in an unhealthy way or to promote an unhealthy culture. Kevin pursued his passions in research and didn't necessarily focus so much on what he thought would generate impact or boost his H-index. And he would probably be sniggering at the back of the room if he heard me talk about the size of his H-index anyway. So I mentioned before that there were, in the early 1980s, there were advancements in stable isotope tracer techniques and mass spectrometry equipment that enabled those using the muscle biopsy technique to study human muscle protein turnover for the first time. So it's, I guess, a quick kind of overview that I felt might be important for some people in the call today is to touch very briefly on what are stable isotopes. it's impossible really to ignore this when we talk about the work of Kevin Tipton. So a stable isotope is a species of an element that's a little bit heavier, contains an extra neutron in the atomic nucleus. Stable isotopes, as the name implies, do not degrade in the same way that the radioactive version of the isotope does, and so they do not emit ionizing radiation and hence are safe for use for the study of human metabolism. The idea with stable isotopes is that they biochemically behave in a manner that is indistinct from their more commonly occurring counterpart. And again, as the name implies, they can be, their fate into biological substrates can be traced. And if we can obtain biological material, mass spec analysis allows us to determine differences in the mass of that sample, and we can start to get a handle on dynamic rates of metabolic flux. Again, apologies for the very text-heavy slide. This is used in some of my teaching in the past, but I've faded out the bottom component of this slide and really focused on the top two applications of stable isotope tracers as they relate to the work of Kevin's that I'll talk about for the next 30, 40 minutes or so. So firstly, we can use stable isotope tracers to measure the direct incorporation or the synthesis into specific polymers. So we can use stable isotope labeled amino acids to measure their incorporation into protein structures. And also there are stable isotope tracers available to measure glucose and lipid metabolism. It's also possible to use stable isotope tracers to measure arterial venous balance to get an indication or a proxy of the synthesis and breakdown flux of or metabolic flux across a limb or a tissue. So if we have a simultaneous measure of blood flow, we can measure the uptake and the release and intermediary metabolism of isotopically labeled compounds. And this can give us important information on how these compounds disappear and reappear in circulation, and hence can be used to get a handle on synthesis and breakdown. Here's an illustration of the previous slide, really. What you can see here in the top right-hand corner are a number of different stable isotope tracers for different substrates. So glucose, lipid, and protein metabolism can all be measured with some of these specific tracers. And this is not an exclusive list of stable isotope tracers, just a few examples for the purpose of this slide. The isotope labeled version is indicated by the red circles and the naturally occurring isotope by the blue circles. So you can see that through intravenous administration or infusion of stable isotope tracers, we get a rapid appearance in circulation that ultimately equilibrates or plateaus before we can take metabolic measurements. Stable isotope tracers are subsequently transported to the from the artery to the intracellular space of in this case, a muscle cell, which is effectively a storage reservoir of sorts for substrate, and subsequently synthesized and simultaneously broken down from intact polymers, such as skeletal muscle proteins, for example. Upon release back into the intracellular free pool, our amino acids, including our isotopes, can be released back into circulation on the venous side, as you can see here. And what Kevin's work mainly focused on over the years was, well, initially in the mid-90s through to the mid-noughties, was sampling from the arterial side and the venous side to understand the dilution of stable isotope tracers to get a handle on aspects of muscle protein turnover. So the rate of disappearance of our stable isotope tracer from the arterial side gives a proxy of synthesis, the assumption being that this tracer is disappearing and for its synthesis and incorporation into muscle protein, and simultaneously the release and appearance of our tracer on the venous side gives us a representation of muscle protein breakdown. Okay. What Kevin was also involved in was pioneering a number of studies that also sampled from the intracellular space, as well as the artery and the vein, to deliver something that was referred to as the three-pool model. Okay, so a more accurate reflection of, or a more accurate way to determine rates of muscle protein synthesis and breakdown. And through his work with Bob Wolf, Kevin was also heavily involved in work determining the direct incorporation of the stable isotope traces into muscle protein to calculate something that we call the fractional synthesis rate, or FSR, so-called gold standard method to measure acute muscle protein synthesis. So if you take sequential biopsies, as indicated by T1 and T2 here, and you're able to detect the enrichment of your stable isotope tracer in those serial biopsies, and you understand the enrichment in a given precursor pool, that could be the plasma or the intracellular free pool, you can calculate a rate of muscle protein synthesis that is expressed as a percentage per hour. So alongside those approaches, I wanted to show you quickly an example of the complex schematic timeline that Kevin and his co-authors in the mid-1990s often used to determine, to conduct some of the first studies on the effects of diet and exercise on muscle protein turnover, and a few images alongside that here as well, including Kevin taking biopsies. You can see a biopsied subject, a volunteer, performing resistance exercise with the IV infusion hooked up at the same time. You can see multiple infusion pumps and infusates hooked up with corresponding lines here as well. And finally, a piece of the muscle biopsy tissue that has been extracted. So this type of timeline was typical of the work that Kevin did throughout the 90s and the early noughties as well. So you can see studies conducted on the order of hours, blood flow measurements, the infusion of amino acid solutions to simulate feeding, fed state effects on muscle, and also a simultaneous infusion of multiple stable isotope traces here to directly determine fractional synthesis rates in muscle, as well as muscle protein turnover through proxies of synthesis and breakdown using 2- and 3-pool models as well. So very, very challenging studies to run, lots of hands required to run these things efficiently. And actually, there are a lot more individuals as a result of these studies that can have the capacity to do this now. Sorry, I'm just looking at the chat while we go as well. I wasn't sure whether somebody was having sound problems or not. But anyway, I won't show too many more schematics, but the vast majority of the studies I'll present today are from a similar acute metabolic investigations as this one, involving procedures that look a little bit like this. So for the next 10 or 15 minutes, I'm going to focus on some of the work that Kevin did between the mid and late 1990s. So I guess these studies are, as I said before, considered to be to have set the agenda for work that has followed over the next 20 to 30 years in the field of muscle protein turnover, and some of, if not the most highly cited studies in this area as well. So I'll go through in a rough timeline order and describe the outcomes of these studies and I guess the important, at the time, groundbreaking information that we were able to glean. A study published by Gianni Biolo involving Kevin back in 1995 was the first to get a handle on how rates of protein synthesis and breakdown and the resultant net balance, that is, whether we are accruing or losing muscle protein, which is the ultimate determinant of muscle protein remodeling. This net balance is critical to that. So how these parameters changed in following resistance exercise compared to rest. So you can see we have an illustration of the three-pool model that was used here. So sampling to determine tracer dilutions at the artery, the vein, and also flux in and out of the intracellular free pool here as well. In response to over several hours after resistance exercise, twofold increase in muscle protein synthesis or protein synthesis across the limb. Similarly, there was an increase in rates of protein breakdown as well, such that the overall net balance of muscle protein remained marginally negative. And the direct measurement of muscle protein synthesis, or FSR, showed similar findings to the 3-pool model, quite a pronounced drastic increase in muscle protein synthesis there. So at the time, some of these data really were considered to be quite surprising. The idea was that you go to the gym, you lift heavy weights, you build muscle. But actually, in terms of the basic metabolic breakdown of that, this finding here that was replicated by the group several times in subsequent years showed that overall net balance it was not positive. And remember, it is that positive balance that's required to increase muscle protein mass and promote hypertrophy over time. Following on from this, again, it had been common knowledge maybe in the bodybuilding world for decades before, but rereading back over this 1997 study from Gianni Biolo, it's really interesting to hear the authors in that introduction talk about the idea that some people are interested to understand the effect that amino acids can have on supporting muscle protein turnover after resistance exercise, because this is now common knowledge that the intake of protein, or the appearance of amino acids to a previously exercised muscle bolsters the muscle anabolic response. But back in the mid-1990s, this was all speculative, really. There was lots of anecdotal evidence to suggest that protein intake can augment muscle hypertrophy, but very little direct metabolic evidence from high-quality, tightly controlled studies like this. So in the follow-on work, Kevin and colleagues determined muscle protein synthesis and breakdown using the 3-pool model again, under conditions of rest in the fasted state, following the IV infusion of amino acids, not the oral consumption, following resistance exercise alone, and then finally following resistance exercise with amino acids infused during the recovery phase afterwards. What you can see on the right-hand side here is the resultant net balance calculations. So effectively the difference between synthesis and breakdown from the figure on the left-hand side. So you can see that the infusion of amino acids promoted a positive net balance across the leg. And in line with the previous work, net balance remained negative with resistance exercise in the fasted state. And finally, the greatest net anabolic response in terms of positive balance was seen when resistance exercise was combined with this IV infusion of an amino acid solution. So intrigued by this, Kevin and colleagues wondered, well, would the response be the same with orally ingested amino acids? And again, in the introduction to the paper, I'll show you here, it's really interesting to see that at one time, there was lots of speculation about whether oral amino acids would actually bypass splanchnic extraction and appear in circulation and present to muscle after exercise. It's strange to think that 25 or so years ago that was an unknown concept. But Kevin led the first study on this question. Again, intrigued to understand whether these amino acids from orally ingested appear in circulation, and whether they direct muscle protein synthesis, and how they also influence protein breakdown and overall net balance. So here is the schematic illustration again. So a study conducted on the order of 7 to 8 hours during a continuous stable isotope infusion. And here are the outcomes. And here's Kevin presenting these data at a conference from way back when as well. I mean, I feel like I'm getting old now, but I'm not old enough to remember a time where we printed out our posters on sheets of A4 and stuck them on a board. This is Kevin presenting those data back in the day as, so effectively printouts of the paper. There's a good chance he lost his poster in the luggage during his flight. That might have happened, but I think this probably reflects the time more than anything else. So yeah, and here are the data anyway. So in terms of protein synthesis, breakdown, and the overall net balance across a limb, you can see quite an intriguing story. And what was unique about this study that was, Kevin also had there was consumption of a placebo beverage orally after exercise, a large 40-gram bolus of essential amino acids, and also a bolus of mixed amino acids, which was effectively 20 grams of essentials and 20 grams of non-essentials. Because another sub-question Kevin was really interested to understand was whether the non-essential amino acids were required to bolster the muscle anabolic response to resistance exercise. The understanding back then was that in response to resistance exercise, there is a breakdown of protein and a release or an abundant supply of non-essential amino acids. And so providing further non-essential amino acids to support synthesis through oral ingestion may not necessarily be required. And in terms of overall net balance, you can see that following resistance exercise with the oral consumption of mixed or essential amino acids, that net balance became positive. And so this led also to the conclusion that perhaps the non-essential amino acids are not necessarily required to support muscle protein synthesis. And again, this is a study that has instigated dozens, if not hundreds of really important follow-on papers over the years as well to understand some of the specifics about protein nutrition and certain essential amino acids, particularly leucine. So the final of the 4 studies I wanted to show from this part of Kevin's career was a piece of work that was led by Stuart Phillips, again, highly cited, and one of the first studies to try to detail the time course of change in muscle protein turnover in response to resistance exercise. So here again, we've got the direct incorporation of the tracer with serial muscle biopsies to generate the fractional synthesis rate, muscle protein synthesis. And on the right-hand side, we have data generated from the 3-pool model to show us what the overall net balance looks like. And all of these studies were conducted in the fasted state. It's important to note here as well. But what you can see is that synthesis is robustly stimulated in the initial hours of recovery after a strenuous, demanding bout of resistance exercise and remains elevated above pre-exercise levels, even at 48 hours after 48 hours of recovery. And that's roughly reflected in the change in net balance, as you can see as well. So net balance still remains somewhat altered even 48 hours into the recovery phase. So a really important study in terms of that, again, has catalyzed a whole host of investigations since to look at how frequently you should train a muscle group to optimize hypertrophy, when you should consume protein around exercise, and so on and so forth. So collectively, 4 studies that have really set the tone for much of what has followed in the next 20 to 30 years. To illustrate the outcomes of those previous 4 studies, I'll show a schematic again here, an illustration that most of you have seen over the years. But in response to a meal containing protein or amino acids, we understood from these 4 studies that there is quite a robust stimulation of muscle protein synthesis that is somewhat transient and falls back down to fasted levels in the hours after protein ingestion. And with repeated feeding throughout the day, we repeatedly stimulate this response. At the same time, there is a lesser suppression of muscle protein breakdown, and this concomitant increase in synthesis and suppression of breakdown results in an overall net protein balance that is, in individuals who are not engaged in structured exercise training, is counterbalanced by net negative protein loss, as you can see in the green shaded areas here as well. But with resistance exercise, the muscle anabolic response to protein nutrition is augmented. There is a synergistic effect, prior resistance exercise contraction, and the provision of amino acids, either orally or through IV administration. And at the same time, there is also, to a lesser degree, some suppression of synthesis. So summarized in the bottom right-hand corner here, with resistance exercise, variations in synthesis are greater in the fed state and decline less in the fasted state. And if you take the overall net balance on any given day in an individual who is engaged in resistance training with higher levels of protein intake, you can see that it gives us a net balance that is positive. And in a very simplistic, gross way, this illustrates the metabolic basis, we think, for muscle hypertrophy over time. Even though this concept has been challenged in recent years, it still remains the best mechanism to explain how we build muscle over time. And again, another way of reflecting the same thing, with prior resistance exercise across any given day, less time spent in negative net balance, more time spent in a scenario of positive net muscle protein balance is going to ultimately lead to the net deposition or the accrual of muscle protein over time. So from those early studies that Kevin led and was heavily involved in, here's the new knowledge that was generated. And hopefully some of the concepts, I'm not going to read each of these out individually, you can all work through them over 30 seconds or so, I guess, but hopefully some of these statements, you can see how profound they would have been at the time. And we're talking about really major breakthroughs in our understanding of how diet and exercise regulate skeletal muscle protein turnover that have informed strength and conditioning, sport and exercise, nutrition, healthcare, muscle remodeling for optimal health in different populations, and a whole host of other important research agendas for the last 20 or 30 years. So what do you do with all this new knowledge? You're in a fantastic research environment, research outputs are coming thick and fast, and you're answering some of the really important questions and gaining a lot of traction. And in terms of the specifics of protein nutrition, once you understand how ingested protein or amino acids regulates muscle protein turnover, you can start to drill down on some of the specifics around things like protein dose, how much is required to optimize muscle anabolism, resistance exercise, the influence of macronutrient content in either isolated protein sources through the addition of carbohydrate or fat, or through protein-rich whole foods that have a more complex food matrix than an isolated supplement powder. You can look at how to optimize the timing of protein nutrition around exercise to optimize these muscle building outcomes, the pattern of protein consumption across a given day. And finally, you can also look at differences in the source of protein consumed for muscle anabolism. Again, with the knowledge that certain sources are deemed to be higher quality than other protein sources in terms of their essential amino acid content and the absorbability of those essential amino acids as well. And in the years, in some of the final work that Kevin did at Galveston, and then during his move to the UK, he pursued some of these questions with quite a lot of focus. So one of the outputs that followed on from some of the initial work that Kevin had undertaken at his time at UTMB was led by Blake Rasmussen. And this was one of the first studies to try to understand whether there is a so-called anabolic window in which to consume amino acids around exercise with a view to optimizing muscle anabolism. So in this study, a relatively small dose of essential amino acids was consumed alongside 35 grams of sucrose. And this drink was consumed either 1 or 3 hours after a bout of strenuous leg resistance exercise. And the resultant net balance was measured here. The top panel are the data for the drink consumed 1 hour after exercise, and the bottom are the data for the drink consumed 3 hours after exercise. And you can see that regardless of the timing, this relatively low dose of essential amino acids plus carbohydrate stimulated muscle anabolism by driving muscle protein synthesis whether the drink was consumed at 1 or 3 hours after exercise. So in this scenario, the timing didn't seem to matter an awful lot. So perhaps some of the earliest work to start to question the idea of a very small anabolic window to consume protein after resistance exercise with a view to optimizing overall net balance. Kevin followed this with a publication the next year, in which he was interested in understanding whether ingesting protein prior to exercise compared to after had an influence on overall muscle anabolism. And so the idea here, again, it's difficult to try and remember a time really where individuals didn't just assume that you consume protein 30 minutes after exercise and that's the best way to maximize at least the early phase muscle anabolic response. But that was the case back in the late 1990s. And Kevin was interested in this idea because the theory was that if you provide a source of amino acids in circulation for muscle synthesis prior to resistance exercise, you can potentially capitalize on the increased blood flow that occurs during the exercise bout to gain a more targeted nutritive delivery to muscle. So a combination of providing amino acids before exercise in a scenario where blood flow is rapidly increased could be greater for muscle anabolism. And so Kevin investigated this question, and the pre refers to the condition in which the drinks were consumed. The drink was consumed prior to exercise and post, obviously following exercise. And you can see in terms of the uptake of phenylalanine or amino acid uptake across the leg over 3 hours of recovery, interestingly, consuming the amino acids before exercise seemed to promote superior muscle anabolic response. And that was also reflected in some of the muscle protein synthesis and breakdown kinetics and the overall net balance segmented over time, as you can see in the bottom figure here, whereby consuming the drink prior to exercise seemed to promote superior muscle net balance compared to following exercise, which was at the time, Kevin told me, was a bit of a head scratcher, but could potentially, as I mentioned a minute ago, could potentially be explained by the idea that nutritive flow would have been greater in the group that consumed their protein prior to exercise. Following on from this, Kevin was interested to understand, was that response they saw before simply due to the fact that free crystalline amino acids were given? And would the response be the same when an intact protein source, I guess what you'd refer to as more commonly referred to as a protein powder, something like whey, was consumed? And so the follow-on study it was published a few years later when Kevin had moved to Birmingham, but nonetheless really important information. Used a very similar experimental design, pre versus post protein consumption, but this time switching to whey as opposed to that free crystalline essential amino acid mix. And in this case, 20 grams of whey protein was consumed. And you can see that regardless of the timing here, muscle protein accretion was stimulated to a similar extent. In terms of, there's a figure on the right hand shows, in terms of phenylalanine uptake over 4 hours of recovery, the groups were indistinguishable. So perhaps some difference compared to the intake of free essential amino acids prior to exercise. Timing of your whey protein ingestion around exercise didn't seem to be as critical for this muscle anabolic readout. So the summary of those previous 3 slides looks something like this, and I've redrawn this illustration from Tyler Churchward-Vinay's review a few years ago now. But the dashed blue curve here indicates the fed state response to the ingestion of protein under conditions where exercise has not been completed. But based on the Stuart Phillips work I showed previously from 1997, we know that there is a pronounced and sustained increase in muscle protein synthesis that persists for up to 48 hours after the original bout of exercise. And so the consumption of protein on top seems to be acting synergy with that resistance exercise induced increase in muscle protein synthesis to result in superior levels of muscle anabolism. So in the post-exercise period, the muscle protein synthesis response to the protein you ingest is enhanced. Now, without doubt, the greatest anabolic window is in the hours around exercise. We can't get away from that. But the point here is that the window is open for a lot longer than was initially thought. So protein consumption with every main meal during a structured resistance exercise training program, frequent bouts performed on a muscle group every week is probably the most important way to go, as opposed to concerning oneself with high quality protein ingestion 30 minutes after exercise and then no further consideration of protein thereafter. In his time at Birmingham, Kevin managed to establish muscle biopsies and stable isotope tracer techniques to study human muscle metabolism. And one of the most important pieces of work Kevin did there that was led by by Oliver Witard and a study we had a lot of fun conducting, was to try and understand how much protein you need to consume to maximize muscle anabolism. So let's track back a little bit. So far, Kevin had done work to understand how muscle protein turnover responds to the oral ingestion of protein, how that occurs in combination with resistance exercise, the timing of protein around exercise and what the anabolic window a true anabolic window might look like. And the question here is all around how much protein. And so in this study, there were 48 individuals in a parallel design assigned to one of 4 groups. So a 0 gram non-protein placebo, right through to a 40 gram whey protein consuming group. So a relatively high dose of whey protein ingestion consumed after a very demanding bout of leg resistance exercise. As you can see, Oliver Witard acting as probably the most inappropriate spotter of all time, I would imagine, given his build, but he was still spotting these very, very strong resistance trained individuals. The figure on the left-hand side shows you the muscle protein synthetic responses in the resting non-exercise limb in the white bars, and also the exercise limb in the dark bars. And so, of course, given the now known synergy between exercise and protein nutrition for anabolism, rates of synthesis at any given dose were always greater in the resistance exercise condition. But the response of muscle protein synthesis, statistically speaking anyway, reached a plateau after the ingestion of 20 grams of protein after resistance exercise. In terms of the fate of the additional 20 grams of protein in the group that consumed the 40 gram dose, measures of urea were taken in blood, and also indications of amino acid oxidation, as you can see in the figure on the right-hand side, were also collected, and it seemed that excess protein was delivered towards oxidation and or excretion, as opposed to its direct incorporation and synthesis into protein. So not the first study, but an important follow-on study to some earlier work from Stuart Phillips to optimize the dose response requirements to maximally stimulate post-exercise rates of muscle protein synthesis in healthy young individuals. I haven't spoken much about endurance exercise so far, and for good reason, but alongside that, the dose response study, we were simultaneously running a study where we were interested in understanding the importance of protein nutrition for the endurance athlete as well. So a lot of Kevin's work so far, at least that I've presented to you, has focused very heavily on resistance and strength training. But one of Kevin, in fact, maybe Kevin's first published paper as part of his PhD thesis was work on muscle protein turnover conducted in female swimmers to show that after a 1 hour bout of swimming in highly competitive female swimmers, there was an increase in muscle protein synthesis. So Kevin had been exploring the effects of endurance exercise on muscle protein turnover for quite some time. And work from Stuart Phillips' group at McMaster University around this time also showed that endurance exercise seemed to stimulate an increase in mitochondrial protein synthesis. So we now had the capacity to tease out different subfractions from muscle and investigate the synthesis of these specific fractions. So myofibrillar, the contractile components of muscle tissue, or the smaller mitochondrial pool of proteins in muscle as well. And so Kevin was intrigued by this work from the Phillips group, and we wanted to understand whether protein nutrition, how protein nutrition influenced the synthesis of these different protein pools following endurance exercise. And we went into this work with the hypothesis that the protein ingestion would enhance the synthesis of mitochondrial protein synthesis. But again, true to form, and really speaks to Kevin's ability to be very kind of self-critical and challenge his own preconceived notions. It didn't quite pan out that way. And we actually got an increase in myofibrillar protein synthesis. Now, one way of interpreting these data are that this increase in myofibrillar protein synthesis after endurance exercise and protein consumption would over time lead to muscle building in these trained cyclists, which perhaps would be an undesirable physiological adaptation in some scenarios anyway. But we took this to mean that the mitochondrial protein pool in muscle was extremely small, is extremely small, and the synthetic needs of the mitochondrial pool are probably taken care of by the amino acids that are provided through protein breakdown. So the amino acids that come from dietary protein sources may not necessarily be required to support the synthesis of this small pool of mitochondrial proteins in muscle. In comparison, this ride was quite demanding and strenuous on these individuals, and although we didn't measure protein breakdown, it's entirely possible that that this increase in myofibrillar protein synthesis with the protein consumption may have been required to help in some way with the recovery of damaged or degraded muscle proteins. So not necessarily indicative of muscle building, but perhaps muscle regeneration and adaptation following this strenuous exercise. Final couple of slides from me, really to try and bring home Kevin's work. After the dose response work that I presented from Oliver Witard 2 slides ago, where we'd come to this idea, similar to Stu Phillips, that perhaps 20 grams of protein is optimal to support rates of muscle protein synthesis after resistance exercise, at least in individuals that weigh around 80 kilos. We were involved in some work that was led by Stu Phillips and Dan Moore to try and determine the relative dose response of protein intake for supporting muscle protein synthesis. So whenever the data on 20 grams of protein were presented at a conference, inevitably you'd get very well-trained big individuals approach you and ask about, wow, 20 grams of protein is not very much, and I could never consume 20 grams of protein and maintain or build my muscle mass over time. And so we decided to take a retrospective look at data that had been collected over years previously. Here we have a number of studies in which muscle protein synthesis was determined in response to a given dose of protein. What we did was went back and expressed this dose of protein relative to each individual's body mass. And the circles here indicate for you the body mass of every subject. Individual subjects. And using a biphase linear regression, we identified a breakpoint that occurred in younger individuals on the left-hand side at around about 0.24 grams per kilogram of body mass of protein required to optimally stimulate rates of muscle protein synthesis. So if you extrapolate that backwards, that's about 20 grams of protein for an 80 kilogram individual. So the maths line up quite nicely. Of course, if you're much larger, then in absolute terms, this dose of protein would be increased. And an important outcome of this work that was also touched upon was that the dose response protein requirements to support muscle anabolism in older individuals are actually increased. Again, aligned to this idea presented some 10 years or so previously by Mike Rennie's group, that older individuals may experience some form of muscle anabolic resistance in older age, where they become less sensitive to the anabolic properties of ingested protein. Following on from that, after his move to Stirling in 2011, again, Kevin liked to set himself challenges, and so it's a whole new research environment, establishing muscle biopsies, stable isotope tracer infusions, trying to answer important questions all these years later. He did a really important work that followed on and really rounded off the dose response question, at least to my mind. Anyway, so here we have some work led by former PhD student of Kevin's at Stirling, Lindsay McNaughton, published back in 2016, to try and get a handle on whether muscle mass affects the dose response requirements of protein to optimize muscle anabolism. So two schools of thought here. Either if you're an individual who has relatively large amounts of muscle mass, then intuitively you might expect that you would require more protein to meet the muscle remodeling response of that muscle, or requirement of that muscle following exercise. The second viewpoint here is that perhaps the amount of muscle mass you exercise determines how much protein you should consume after exercise to optimize the remodeling of different tissues. So again, important context here is going back to all the other studies. Often the resistance exercise stimulus was isolated to the lower limbs. In the McNaughton study, the resistance exercise stimulus was whole body. And in this study, volunteers were recruited who had low lean body mass, so relatively light individuals. So the low lean body mass group were probably about my body weight, around 80 kilos, with about 60 to 65 kilos of lean tissue mass. And those with higher lean body mass in this study were the so-called bigger individuals, weighing close to 100 kilos, with somewhere close to 80 kilos of lean tissue mass as well. So large amounts of lean body mass. And in terms of muscle protein synthesis in those myofibrillar contractile proteins, regardless of muscle mass, big or small, regardless of whether the dose response didn't seem to differ, whether 20 or 40 grams of protein was consumed. When all those data from the different body mass groups were collapsed together, you get something like this figure on the right-hand side here that shows you that there is a small, albeit significant, increase in muscle protein synthesis in the group that consumed 40 grams of protein after exercise. So the take-home message from this study really was that this 40-gram dose of protein, when consumed after a whole body workout, seems to be more effective for stimulating muscle protein synthesis than the lower dose. And thereby, regardless of how much muscle mass you have, perhaps it's the muscle mass that you exercise during a training session that determines how much protein you require to achieve optimal levels of remodeling. So again, I'll just put the summary of the new knowledge generated from the latter part of Kevin's career here. Again, hopefully you can see that these contributions have really shaped the sport and exercise nutrition literature, and probably also to some degree the practice as well. What I would also say is that I think I've presented data up until 2016 here, and despite struggles with health, I want to highlight that even as late as 2021 and even publishing in early 2022, Kevin's mind was, well, at least as I saw it anyway, he would always tell me different, but was always as sharp as it had been to me, and he was still functioning to an extremely high level and producing research outputs, particularly some of these important research reviews here, that I think really signpost us to important directions for future research as well. So I highlight these papers because I think some of the ideas put forward here are well worth revisiting, and I hope will instigate strong research focus for the next generation of those who would like to work in this field. I'll summarize, not too much really, again, because I'm not sure Kev would have necessarily liked me talking in such terms about him. He would definitely have been crying at the back of the room anyway, but I think it's important to summarize all this by talking about Kevin's legacy and trying to summarize everything and give a picture of what it looks like. So I think the first part of Kevin's legacy really is all about the individuals he trained. So the research groups he established from scratch, the time, generosity, and effort he gave into training, training those around him as well, was truly inspirational. And so, many of the individuals in the images you can see here that he's trained over the years are now leading their own research groups, working heavily in muscle protein turnover with exercise and nutrition. Beyond those that Kevin worked directly with, he spoke global conferences, was often the headline act. As I mentioned before at the offset, an engaging, enthusiastic speaker who, often at great cost to his own professional life, would take a lot of time to sit and engage with individuals outside of his talk and formal Q&A. I would often at conferences arrange to meet Kev and find myself sitting at a table with a group of PhD students from some far-flung corner of the world that he'd befriended, and he'd often be holding center court, telling them all about his experiences and trying to impart some of his wisdom as well, extremely generous in that regard. And that also extends to his teaching. I've not touched on it very much, but Kevin was an outstanding lecturer, teacher, receiving several teaching commendations at every institute he worked at over the years. He was always the favorite lecturer of every of the students he taught on exercise, metabolism, and nutrition. And again, there are students Kevin taught at undergraduate level that are now have pursued a PhD and are leading their own research groups, again, inspired by his lectures. And in terms of translation of science to practice, Kevin was a keen advocate of this. It wasn't a case of producing strong experimental evidence and then going back to the lab and kind of hiding out. Kevin was very keen to project himself and worked with major governing bodies and institutes across the world, as I've highlighted some here. That's not an exclusive list, but there was a strong commitment to ensure that the science he generated was translated to practice as well. And I think in addition to his strong academic output, his enthusiasm in this area has also really feeds into his reputation. And I think the huge response that was seen at Kevin's passing is due to all of these factors. So in terms of legacy, I think this is probably the best that any of us in academia can hope for in terms of career output. And so, yeah, hopefully some inspiration for the next generation there. But I'll close up, I think, just on the hour. And thank you all for your attention, especially those who've tuned in from a distance over Zoom, and happy to answer any questions. Thank you.
So, well finished off. Thank you. Have you got any questions in the room from anyone? We've got one question up here. Well, we've got a clap.
I'll take a virtual clap.
That's a virtual clap. Thank you very much. Thanks, Nick. I've got a couple of questions. If no one else has, I'd rather others take up the time. But if you can't answer it for Kevin, then answer it for yourself. But one thing you didn't really touch on, perhaps, and maybe Kevin had got a question. Yeah, one sec. I'll finish off my question, and then I'll come to your question. Was around protein supplementation, because obviously you touched on dose, and there's no point going over a certain dose, but whether he had a view, and I'm sure he did, of whether it needed to be whole food or protein supplementation, because you didn't really get onto that, and of course you didn't have time to do that. Whether he had a view or whether you have a view on that. Yeah,
Kevin was pretty pragmatic about where you get your protein from. I know that he was an avid consumer of supplements, particularly during the time that he trained more regularly as well, before health issues got in the way. But again, I think speaking to Kevin's ability to challenge his own preconceived notions, I saw Kevin's thinking change over the years from this idea that perhaps whey protein, something that's high quality and enriched in essential amino acids, is absolutely the only way to go several times a day, to a position whereby there are potentially important muscle anabolic properties that can be found in a whole food matrix as well. And again, I think some of the work that Luke Van Loon and Nick Bird and others are doing in well-recognized protein turnover labs across the globe are doing at the moment has started to shed light on some of those important issues. And again, I think that's work that wouldn't have happened, I don't think, without some of the important studies that Kevin conducted in the 90s at UTMB. So his position changed over the years and moved more towards, if you can get the protein from whole foods, if it's convenient, if it's high quality, so enriched in essential amino acids, particularly leucine, then you can consume whole food, protein rich around your resistance exercise, and really your muscle adaptive remodeling response shouldn't really be hurt too much compared to if you were consuming only whey protein supplements as well. But he was very much intrigued by and interested to follow some of the work that has been, as I say, that's been kickstarted in the last few years, starting to uncover some of the muscle anabolic properties of some of the compounds that we find in whole foods as well, which I don't think has been, well, I think we're probably just scratching the surface of that at the moment, in terms of some of these important species that may be present.
Sorry, Nick, were you pointing something out that I missed?
No, I was just checking that.
Okay, great. Is anyone either online or or in the room got any questions for Leigh, either about protein and or Kevin specifically? I have one more question. Always got questions. I think it was your work, or maybe not. Sorry, but the mitochondrial. So when you got into mitochondrial fraction, you didn't see that difference. But were you surprised? And do you have any insight that you didn't, given that they were working at 70% of the max? Because and is there anything that you measured that would highlight why mitochondrial protein synthesis was not not increased with the protein?
So we one of the frustrations with that study, and it was definitely a bugbear of Kevin's when we were conducting that as well, was in terms of financial support and resource. We omitted taking a resting muscle biopsy sample after 2 or 3 hours of infusion prior to exercise to determine resting rates of muscle protein synthesis. So we had no idea pre-exercise what the rates of mitochondrial protein synthesis look like. So it's difficult to say in that study whether the rates you saw in the figure were a stimulation compared to pre-exercise or not. I mean, there's every evidence to suggest, again, follow-on work over the years focused on the mitochondrial protein pool seems to indicate that it would have been an increase compared to basal pre-exercise levels, but we really can't be sure about that. But it's an inherent design flaw. One of those things that we spoke about a lot. We definitely kicked it around. In terms of why protein didn't bolster that mitochondrial synthesis response, I touched briefly on the fact that we think it's the mitochondrial pool, typically 5 to 10% of all muscle protein, extremely high rates of turnover compared to something like myofibrillar proteins. And so we put forward the idea that in response to that particular endurance exercise stimulus, there may have been an increase in the appearance of amino acids in circulation as a result of some form of breakdown, muscle protein breakdown, and that those amino acids that appeared as a result of breakdown were effectively resynthesized, reincorporated back into that mitochondrial pool, and effectively that took care of the requirement, the amino acid requirement to synthesize that mitochondrial pool. And it feeds back to, again, the really early work I mentioned with Kevin's around protein ingestion or resistance exercise and protein ingestion. There was this idea really that you might not need the non-essential amino acids to support synthesis because they're released as a result of breakdown from the exercise. And the idea I'm putting forward here with the endurance exercise and mitochondrial is very similar. It's a very small pool of protein, and potentially the breakdown response you get from the endurance exercise bout takes care of the synthetic requirement.
Leaving the intracellular pool, is that?
Yeah,
just recycled. Has there been any evidence?
Leaving the pool. Leaving the pool and appearing in the venous side,
and coming back,
full circulation and being reincorporated in, potentially. And
has there been any evidence to sort of support that since? Future studies.
There's been some. There's been work, again, follow-on work, probably with a more practical and applied angle from John Hawley's group in Australia. Some work that Donny Camara has led has come to a relatively similar conclusion that actually it seems to be following endurance exercise, the myofibrillar protein pool seems to be most responsive to the protein that you provide after exercise. The mitochondrial proteins do not really appear to be tapped into that much. And I think there might have been a review from maybe 1 or 2 years ago, maybe more, time flies, but maybe you were involved in something as well where there was a summary of there was a summary of whether this mitochondrial pool of proteins in muscle is actually amino acid responsive or not. So some of the very early work in fusing amino acids found an increase in mitochondrial protein synthesis, and that was done by a group in France. Certainly, but in terms of post-exercise with oral protein feeding, that mitochondrial protein pool doesn't really seem to respond very robustly, at least not in a way we can detect.
Yeah, I guess that's the problem, isn't it? Detecting it if it's such a small pool. Okay, thank you. I won't ask any more questions. I can chat to you offline, of course. No one in the room has got any questions. I think everyone's just complimenting you online, so I think you got off lightly there.
Well, I can always blame someone else's work, right? I can always Kev would have laughed if I just blame Kev.
Exactly. So again, just big thank you from everyone online, obviously, and everyone in the room for taking the time to tell us a bit about Kevin and remind us how important his work clearly is or was, whichever way you want to put it, the contribution of this particular field. So thanks again.
Welcome.